Now we come to the final video on visual and intuitive topology, which is the second subsection of the topology playlist. The first subsection we had considered the foundations, mathematical foundations for topology. Now we've been looking at visual and intuitive topology, just familiarizing ourselves with some general concepts of topology without having to do the serious math. But after this, we can now begin to go into some core areas. I think after this, we'll go take another subsection that is like about metric space topology, and we'll look at the topics under that. So, in this last video, under visual and intuitive topology, we're looking at the historical development of topology. How did we come about the field of this aspect of mathematics called topology? So, from Euler's bridges to modern topological spaces, that's how the journey has been. Topology developed gradually from questions about geometry, networks, surfaces, continuity, and all that. So that is how it all started, and the properties of spaces that remain unchanged under continuous deformation. In this lesson, we trace the development of topology through five major figures rather. Interestingly, on social media and even on this YouTube channel, I have a series on inspiring mathematicians, starting from Imhotep and Ahmes in Egypt, and then all the early people like Sneedles and Thales of Miletus, Pythagoras, and the rest of them. So, but these are the key figures associated with topology. So you have Leonhard Euler, which is the Königsberg bridges problem and graph theoretic ideas. I think this is a very popular problem, like trying to connect the city of Königsberg with bridges also. Then you have the August Ferdinand Möbius. Of course, we'll be talking about the Möbius strip a lot. The Möbius strip and non-orientable surfaces is what that deals with. Then you have the Henri Poincaré, uh, algebraic topology and topological invariants. Then you have Felix Hausdorff, the axiomatic foundations of topological spaces. And of course, you have Luitzen Egbertus Jan Brouwer, invariants of dimension, fixed points, and topological degree. So the learning objectives by the end of this lesson, you should be able to explain how topology emerged from problems in geometry, describe Euler's contribution to topology and graph theory, explain why the Königsberg bridges problem was historically important, construct and analyze the Möbius strip, explain the significance of Poincaré's work in algebraic topology, understand the idea of a topological invariant. I mean, we saw the concept of topological invariant in the last video, bordering on topological properties. So these are properties that help us to see which spaces are homeomorphic or not. Explain the Hausdorff separation axiom, describe Brouwer's fixed point theorem, and explain the significance of invariance of domain. Then connect historical developments to modern topology. Now, the question is, why did topology develop? Why? Before topology became a formal mathematical discipline, mathematicians primarily studied quantities such as lengths, angles, areas, volumes, slopes, curvature, and distances. And that's why I made a playlist earlier on this channel on lengths, lengths, areas, and volumes. So talking about measuring these kind of things in objects. So these are important geometric measurements for sure. But topology asks a different question. Topology doesn't worry about the whole measurement thing. It worries about some other things. So topology asks a different question. Which properties of a space remain unchanged when the space is continuously deformed? Uh, so imagine a rubber sheet that can be stretched, compressed, or bent without tearing or gluing. So it tells you that when we talk about continuous deformation, we're talking about stretching, compression, bending, even twisting. But then we don't, tearing and gluing are not part of the story. So acceptable topological actions will be things like stretching, compression, bending, twisting. But topologically unacceptable actions will be tearing or gluing. So under such deformations that are acceptable, a circle can become an ellipse. Of course, a square can become a rounded shape. A coffee mug can be deformed into a torus. A sphere can be stretched into an ellipsoid. So, however, some properties remain unchanged. For example, a sphere has no hole, while a torus has one essential hole. Thus, topology gradually emerged as the study of qualitative properties of spaces that survive continuous deformation. So you can say topology is the study of qualitative properties of spaces that survive continuous deformation. So a major historical feature of topology is that its questions often began as concrete puzzles and eventually led to the abstract mathematical theories. So let's look at a timeline of early topology. The development of topology was not the work of one mathematician. It was a sequence of ideas developed over several centuries. In 1736, for instance, Leonhard Leonhard Euler, contributed ideas relating to the Königsberg bridges problem. Then you have in the 18th century, the same Euler talked about polyhedral formula and combinatorial ideas. Then in the 19th century, you have Augustus Ferdinand Möbius strip and non-orientability. Then you have 1895, Henri Poincaré, uh, analysis, situs, and algebraic topology. In 1914, it's getting closer. You have Felix Hausdorff, axiomatic theory of topological spaces. In the early 20th century, you have L.E.J. Brouwer, fixed point theorem, and invariance results. So I think Euler was Swedish. It was Swiss, I think. Mobius should be German, I suspect. Henri Poincaré, French. Felix Hausdorff, I think, is German. Brouwer, I'm not sure. The historical progression, I mean, maybe we'll see it as we go on. The historical progression can be summarized as this. We have concrete geometric puzzles leading to combinatorial ideas, leading to topological invariants, leading to abstract spaces, and then we have modern topology today. So each stage expanded the meaning of the word space. So let's start with Euler, who had contributions to so many aspects of mathematics. So Euler was one of the most influential mathematicians in history. Although topology did not yet exist as a formal subject during Euler's time, several of his ideas became foundational to topology. One of the famous examples is the seven bridges of Königsberg problem. The city of Königsberg was divided by the Prager River into regions connected by seven bridges. So the problem was, is it possible to walk through the city and cross every bridge exactly once? So is there a way you can walk through the city and just and cross every bridge, every of the seven bridges exactly once? So let's see the seven bridges of Königsberg, right? Seven bridges. Seven bridges. Königs. Yeah, right here. So this is the bridge problem. Yeah, let's see it in Wikipedia, in fact. Yeah, this is what this looks like. So you have the city right here, and then you have one, two, three, four, five, six, seven. So is there a way you can, you just use each bridge exactly once? So that was a problem back in the day that led to one of the advances here. So this is an idea of what that looks like. So you're traversing the whole city, crossing seven bridges. So these are like the bridges now. A, B, C, D, E, F, G, like that. So all that led to some concepts in topology. So the problem was, is it possible to walk through the city and cross every bridge exactly once? Earlier studied Euler studied the problem in 1736. His crucial insight was to ignore irrelevant geometric details. So instead of worrying about the exact length of the bridges, the shapes of the islands, the positions of the bridges, he represented each land region by a vertex and each bridge by an edge, just like what we saw here. Like, uh, you know, each bridge is an edge and each island is a vertex in that sense. So, okay, yeah. So this produced a graph. The problem therefore became a question about connectivity rather than geometry. So this was a revolutionary idea. Euler showed that the original problem had no solution. The important historical lesson is that the precise geometric shape of the city did not matter. What mattered was how the regions were connected. This is strongly aligned with the philosophy of topology. So, I mean, topology doesn't worry about how long is this, how short is that. No, it's just concerned about how connected are things, basically. So the Königsberg bridges and vertex degrees now. In graph theory, the degree of a vertex is the number of edges incident to that vertex. So for the Königsberg graph, the four land regions had degrees 3, 3, 3, 5. So thus all four vertices have odd degree. So Euler theorem for Eulerian trails tells us that, interestingly, I have a playlist on network and graph and network theory. You want to check that out if in case you're interested in that. So Euler's theorem for Eulerian trails tells us that a connected graph has an Eulerian circuit if every vertex has even degree. So a connected graph has an Eulerian trail using every degree exactly once if exactly two vertices have odd degree. So if more than two vertices have odd degree, like what we have here, then no such trail exists. So since the Königsberg graph has four odd degree vertices, so four is bigger than two, there cannot be a walk that crosses every bridge exactly once. So you may have to cross one or two bridges more than once. So why this was topologically important, Euler had transformed a geometric problem into a combinatorial problem. So the exact positions of the bridges were irrelevant, only the connectivity structure mattered. So this idea became fundamental to topology. So ignore geometric measurements when the question depends only on connectivity. We don't care how long or short anything is, we just care how connected things are as far as topology is concerned. So consider the graph with vertices A, B, C, D and edges A, B, B, C, C, D, and D. This is a cycle because you have A, B, B, C, C, D, D. So it's like you end up where you started from. That makes it a cycle. So all of this is well documented under the playlist on graph and network theory. You want to check that out. So each vertex has degree 2. So degree A is equal to degree B equals degree C equals degree D, and that is 2. Therefore, every vertex has even degree. Hence, the graph contains an Eulerian circuit in that sense. So one possible circuit can be A to B to C to D to A. So now consider a graph whose vertex degrees are 3, 3, 2, 2. Exactly two vertices have odd degree like this. So therefore, the graph has an Eulerian trail, but not an Eulerian circuit. So the historical importance is that Euler reduced the problem to a simple invariant parity of vertex degree. So the actual geometry of the graph is irrelevant. And then we have something like this. So you have Python for Eulerian graph. So exploring Euler's ideas with Python. So in this case, we need network. We need to import network X, the net connectivity library in Python, and then we visualize with matplotlib. So you create a cycle graph. So I mean, because everything, what we have seen that those parts are cyclic. So we have nx the cycle graph with 4 vertices, then relabel vertices. So you have G, 0 is A, 1 is B, 2 is C, and 3 is D, like that. Then you display vertex degrees. So you print the degrees like that and check whether the graph has an Eulerian circuit and draw the graph like that and print a graph with an Eulerian circuit that way. So we run this and then we have the results down here. So for A, 2 vertices, B, 2 vertices, C, 2 vertices, D same. But the Eulerian circuit is true because all the edges are have vertex 2. So the graph then is shown this way. So you have a graph with an Eulerian circuit now. So you have A, so from A, 1, 2, B, 1, 2, C, 1, 2, D, 1, 2. So if I mean this is given like a random thing, but anyhow it comes out because we're dealing with topology. It doesn't matter how it comes out as far as that as far as there's consistency in how these things appear. Okay, so we have Euler and polyhedra. Euler also studied polyhedra. For many convex polyhedra, he observed the relationship V minus F plus V minus E plus F equals to where V is number of vertices, E is number of edges plus F number of faces. So it sees that for many convex polyhedra, this works. So V minus F plus F is always 2. So for instance, if you take a cube has 8 vertices, 12 edges, and 6 faces for a cube for sure. Therefore, V minus E plus F is 8 minus 12 plus 6. And that is 8 minus 12, that's minus 4 plus 6, that's 2. For a tetrahedron, V is F, E is 6, F is 4. So we have 4 minus 6 plus 4, which is actually 2. Then the quantity chi, that is V minus E plus F. So later became an example of an Eulerian characteristic, which, I mean, we talked about this in the last video. It is one of the ways to decide. It is one nice topological invariant we can use to determine homomorphism and all that. So the Euler characteristic became one of the most important topological invariants. For many surfaces, it provides a numerical quantity that helps distinguish different topological structures. So that by calculating the Euler characteristic between two spaces, you can easily decide if they are homomorphic or homomorphic or not. where homomorphism means that the spaces are topologically equivalent. So then we move on to August Ferdinand Möbius from 1790 to 1868. So he came later than Euler. Euler for Euler it was 1707 to 1783. 1707 to 1783. So Möbius came after Euler had died. So August Ferdinand Möbius was a German mathematician and astronomer whose work contributed significantly to geometry and topology. So one of his most famous mathematical objects is the Möbius strip. The Möbius strip can be constructed from a rectangular strip of paper. So you start with a rectangular strip, give one end a half twist, and join the two ends together. So instead of looking like a cylinder, it now looks like so normally it should be like this cylinder, but to join it up, you have to turn it in, and then you have this strip this way. So this is what the Möbius strip looks like here, like this. So with that in place, then um the resulting surface has remarkable properties. The Möbius strip has one side, one boundary component, a half twist, non-orientability. So the half twist causes the non-orientability. This was important because it challenged ordinary geometric intuition. A normal cylindrical strip has two sides. So a Möbius strip has only one continuous side. So if you draw a line along the middle of the Möbius strip without lifting your pencil, you eventually return to your starting point after traveling across what appears to be both sides of the original strip. So you travel along both sides of the original strip, which is quite uh not not normal in a sense, right? So if you let's say imagine moving from here. So this is like the outer side, and then you move around, you keep moving around this, and by the time you come here, like you're moving inside, so the direction is reversed in that case. That is how it is. We say it is non-orientable in that sense. So non-orientability. So a normal cylindrical shape. Okay, if you draw a line, okay, we've talked about this also. This is an example of topological property that cannot be removed by ordinary stretching or bending. If you want to correct that, you have to tear something and reglue. So, and that is not topologically acceptable. So, understanding the Möbius strip now, a standard parameterization of the Möbius strip is x of u comma v is 1 plus v over 2 cos u over 2 cos u. Then the y component, you have 1 plus v over 2 cos u over 2 sine u. And then the z component uv, z of uv is v over 2 sine u over 2. And u takes values from 0 to 2 pi, while v takes values from -1 to 1. So the parameter u moves around the central circle, while the parameter v moves across the width of the strip. So the factor involving u over 2 creates a half twist. So the key observation is this: when u is 0, the strip begins in one orientation. When u is 2 pi, the cross-section has rotated by pi. So when the strip returns to its original location with the opposite, does the strip returns rather to its starting location with the opposite orientation. This is the source of its non-orientability. And then we can use this Python code to demonstrate that, which we've done in previous videos, by the way. So you use something like this, and then you come up with the Möbius strip, which is the gift Ferdinand August August Ferdinand Möbius gave to us in topology. Then we go ahead to the French guy called Henri Poincaré. I'm sure he's French. So Henri Poincaré transformed topology into, so he came 1854 to 1912. So I'm trying to see the overlap, if there are overlaps. 1854. Okay, yeah. Ferdinand was almost going when Poincaré came. 1854. That's 14 years before Möbius died. So Henri Poincaré transformed topology into a much deeper mathematical discipline. His 1895 paper, Analysis Situs, is regarded as one of the foundational works of algebraic topology. So Poincaré's central idea was to associate algebraic structures with geometric spaces. Instead of asking only, what does this space look like? We can ask, what algebraic information can we extract from this space. So this allows complicated spaces to be studied using algebra. So Poincaré investigated concepts related to homology, Betti numbers, the fundamental group, topological invariants, manifolds, Euler characteristic. This represented a major change in mathematical thinking. Topology was no longer merely the study of unusual surfaces. It became a systematic theory of spaces and the relationships between them. So, uh, then the concept like detecting holes now come up. Consider three familiar spaces: a sphere, a torus, and two disconnected circles. Their structures differ topologically. A sphere has no one-dimensional hole. A torus has one tunnel through its middle and another hole associated with its surface structure. So a pair of disconnected circles has two connected components. So topology attempts to capture such differences using invariants. For example, the number of connected components can be represented informally by B naught. For a connected space, that's the Euler characteristic. For a connected space, now you have beta naught or the Betti number actually. So for a connected space, beta naught is 1. For two connected components, beta naught is 2. So the first Betti number, B1, measures independent one-dimensional cycles. So for a circle, you have B1 to be 1. For a sphere, B1 is 0. Then for a torus, B1 is 2. So these numbers help distinguish spaces that cannot be continuously deformed into another because they don't have the same Betti numbers. So then we have the Poincaré and the fundamental group here. So one of Poincaré's most important ideas was the fundamental group. Informally, so I mean this is algebra coming into the whole story, right? Informally, imagine drawing closed loops on a space. Some loops can be continuously shrunk to a point, other loops cannot. I mean, we saw that with a disk. A circle cannot be shrunk, but a disk can be shrunk like that because when its radius is that of a circle, it coincides with the circle. But when the radius becomes smaller and smaller, because the radius can be less than or equal to a particular value of r. So some loops can be continuously shrunk to a point, other loops cannot. For example, on a sphere, every closed loop can be continuously contracted to a point. Thus, the sphere is simply connected. On a circle, however, a loop that goes around the circle cannot be shrunk to a point while remaining on the circle. This difference can be encoded algebraically. So the fundamental group of the circle is actually, for a circle is homeomorphic to the integer system, the set of integers. Then the integer records how many times a loop winds around the circle. For example, 0, 1, -1, 2, and -2 represent different winding numbers. This was a profound development. Geometric loops leading to algebraic structure. That principle is central to algebraic topology. We are going to deal with algebraic topology as we progress. So we have Felix Hausdorff, 1868 to 1942. So I think he must have overlapped significantly with the last guy we considered. Poincaré, 1868 to 1942, right? 1868. Aha, he was born 14 years after Poincaré, but he was born the same year Möbius died. So that's Felix Hausdorff. So a kind of replacement for Möbius. So, and then he lived 30 years after Poincaré died. So Felix Hausdorff played a central role in giving topology an abstract axiomatic foundation. His 1914 book, Grundzüge der Mengeler, that's German, I'm not sure if I did that well, was highly influential in the development of set theory and topology. Hausdorff helped formalize the concept of a topological space. A major contribution was the Hausdorff separation axiom. A topological space is called the Hausdorff if any two is called Hausdorff rather if any two distinct points can be separated by disjoint open neighborhoods. Suppose x and y are distinct points and x is not equal to y. Then there exists open set U and V such that x belongs to y, x belongs to u rather, and y belongs to v. And u intersection v are non-empty, are empty rather. Symbolically, x is not equal to u implies that there exists uv open such that x belongs to u and y belongs to v, and the intersection of u and v is empty. So this property captures an important intuition that distinct points should be topologically distinguishable. So that's one big concept of Hausdorff that a topological space is called Hausdorff if any two distinct points can be separated by disjoint open neighborhoods, like we see here. So most familiar spaces include the one-dimensional real number system and the n-dimensional real number system, and they are seen as Hausdorff. So we have this example right here. So it's separating two real numbers. How do you do that? Consider two distinct real numbers. X is 2, Y is 5. We want to find disjoint open neighborhoods around them. So if you choose U to be 1, 3, so 2 belongs to this open interval, and V is 4, 6, 5 also belongs here. So we see then that 2 belongs to U and 5 belongs to V. Furthermore, the intersection of U and V, so if you intersection of U and V is empty. Therefore, we say the real line satisfies the Hausdorff property like that. So more generally, if X is less than Y, we can choose epsilon, which is less than Y minus X all over 2. Then the open intervals will be U equals X minus epsilon, comma X plus epsilon, and V is Y minus epsilon, comma Y plus epsilon, which are disjoint. So this simple property has important consequences. For example, in Hausdorff spaces, limits of sequences are unique. Then we go on to talk about Luitzen Egbertus Jan Brouwer, 1881 to 1966. Okay, 1881 to 1966. I'm trying to see 1881. So he was born 13 years after Hausdorff was born. So Hausdorff was 13 years older than him. And then he lived up to uh, up to 12 years after Hausdorff died, right? So Luitzen Egbertus Jan Brouwer was one of the major founders of modern topology. His work addressed deep questions concerning continuous maps, dimension, fixed points, degree theory, manifolds, invariants. Two of his most famous results are the Brouwer's fixed point theorem, invariance of the domain. I'm sure we are going to see that as we go on in this playlist. So these results demonstrate how topology can produce powerful conclusions without requiring explicit formulas for distances or angles. Okay, of course, we have the Brouwer's fixed point theorem here. The Brouwer's fixed point theorem states that every continuous function from a closed disk to itself has at least one fixed point. So for the two-dimensional disk, d squared, for a collection of x and y, such that x squared plus y squared is less than or equal to 1, if f maps d squared to d squared, so if a disk is mapped to a disk, is continuous, then there exists some points p in d squared such that f of p is equal to p. That's the idea of a fixed point. So the point p is called a fixed point. So the intuitive example is this, that if you imagine stirring a cup of coffee. So suppose the coffee surface is represented by a disk and the stirring motion continuously moves every point of the disk to another point. So Brouwer's theorem says that there must be at least one point that ends up exactly where it started. So the theorem is remarkable because it guarantees the existence of a fixed point without telling us where that point is. So we have a one-dimensional analog. Imagine for a continuous function f which maps 0, 1 to 0, 1, there must be, that's close to 0, 1 to close 0, 1. There must be some x belonging to 0, 1 such that f of x is equal to x. So a continuous function on an interval now. So consider f of x equals x squared on the interval, on the closed interval 0, 1. We seek a fixed point f of x equals x. Therefore, we say x squared is equal to x. So if we rearrange this, we have x squared minus x equals 0, so that x is equal to 0 and x is equal to 1. And this both of these numbers are fixed points. So x is 0, x is 1 are both fixed because f of 0 is 0 and f of 1 is also 1. So this example is simple enough to solve algebraically. Brouwer's theorem is much more powerful because it guarantees the existence of fixed points for broad classes of continuous functions. Even when solving f of x equals x exactly, maybe explicitly rather, may be impossible. So we have a Python demonstration, finding a fixed point numerically, numerical exploration of a fixed point. So if you cannot, this was easy to find, right? The fixed point for x squared, f of x equals x squared. So it's just equate to x and you find easily. But when it becomes difficult, you may need to use numerical analysis. And here we still use the simple case of f of x equals x squared, and we have x defined from 0 to 1, that close interval, f is x squared. Then we plot x against f and we plot x against itself, and then we do all the plotting and blah blah. And we talk for the fixed point satisfying f of x minus x equals 0. This is us, that same setup we have up there to get the values of 0 and 1 we got. So here now, f of x equals x squared. This is it here. Then y equals x, that's f of x equals x. We have this line now. So, and you see, we have 0, 0 that we got, and we have 1, 1 that we also got there. So we have those 2 points there. So approximate fixed points here, you have 0, 0.002, and all this all the way to 1 like that. We have those fixed points. So then you have the Brouwer's invariance. Brouwer's invariance of domain. So another profound result associated with Brouwer is the invariance of domain theorem. Informally, it says that if a subset of n-dimensional Euclidean space is continuously and injectively mapped into Rn, then its image behaves like an n-dimensional open set, where U is a subset of Rn is open, and F which F maps U to Rn is continuous and injective, then F of U is open in Rn. So this has a remarkable consequence. Dimension cannot be changed by a sufficiently nice continuous one-to-one deformation. For example, a genuinely two-dimensional open region cannot be continuously and injectively transformed into a one-dimensional open interval. This result helps establish dimension as a fundamental topological concept. So let's compare the key figures now. Let's see what they did side by side. Euler talked about bridges and polyhedra, and he introduced combinatorial thinking into geometric problems. August Ferdinand Möbius came up with the idea of the Möbius strip and revealed non-orientability and unusual surface structures. Henri Poincaré talked about fundamental group and homology. He established algebraic topology. Then Felix Hausdorff talked about topological axioms and provided an abstract framework for topology. Then Henri Brouwer talks about fixed point and invariance, developed deep results around continuous maps and dimension. So the progression is important. Euler asked, how are objects connected? Möbius demonstrated surfaces can have unexpected global properties. Poincaré asked, can geometry be encoded algebraically? Hausdorff asked, what axioms define a general topological space? I think there's something about the French and and algebra, right? Because it was Ren Descartes who connected algebra with geometry, and that's how we have the Cartesian coordinate system and all of that. So Hausdorff asks, what axioms define a general topological space? Brouwer established what must remain true under continuous maps. Together, these ideas help transform topology from isolated geometric puzzles into a general theory of spaces. So the evolution of the concept of space now. The historical development of topology can be viewed as an expansion of concept of space. So in stage 1, we talk about geometric objects. Each questions concern concrete objects like polygons, polyhedra, surfaces, and networks. And in stage 2, we have combinatorial structures. Euler demonstrated that some geometric questions depend only on connectivity. Thus, geometry can lead to combinatorics. Then stage 3, global surface properties. Möbius showed that surfaces can possess properties such as non-orientability that are not obvious from local measurements. Thus, local geometry imply global structure. Then we have algebraic topology. Poincaré associated algebraic objects with spaces. The space implies algebraic invariant. Then stage 5, you have abstract topological spaces. Hausdorff and others developed axiomatic approaches. The space no longer needed to be visualized as an ordinary geometric object. It could be an abstract set equipped with a topology. Then in stage 6, now we have topological mappings. Brouwer studied what continuous mappings preserve. This produced powerful results about dimension, fixed point domains, and manifolds. The modern concept of topology emerged from all this progression, all the way from geometric objects to combinatorial structures to global surface properties to algebraic topology to abstract topological spaces and topological mappings. Now, all up to now that we now begin to talk about topological data science. So, so imagine this the case of a circle and an ellipse. Consider a circle, x squared plus y squared equals 1, and an ellipse, x squared over 4 plus y squared over 1 equals 1. So they have different geometric measurements for sure. For example, their horizontal diameters differ, their circumferences differ, their curvature distributions also differ, but topologically both are equivalent to the circle S1, like that. So an explicit continuous deformation is this f sub t of x comma 1 is 1 plus tx comma y. So where t takes value from 0 to 1. At t equals 0, we have f sub 0 of x comma y, which is xy, which gives the original circle. At t equals 1, we have f sub 1 of xy, which is equal to 2x comma y, which produces an ellipse. So no tearing or gluing is required. We just have the circle transforming. I mean, I'm going to demonstrate it using Python code next. Therefore, the circle and ellipse are homeomorphic in that case. This illustrates the central philosophy of topology. Shape can change while topology remains unchanged. So, and if you're interested in geometry, the measurements, as the shapes are changing, the measurements can change in some sense. So imagine Python for continuous deformation, visualizing a continuous deformation from a circle to an ellipse. So we define our theta, taking value from 0 to 2 pi, 360 degrees that is. Then we fix the axis. So for axis and t in, we zip the axis together, 0, 1 over 3, 1, 2 over 3. That's points starting from 0 to 1, because we know t takes value from 0 to 1, like that we have here. So, and as the value of t increases, we see the circle transforming step by step into we see this circle transforming step by step into different ellipses like that. Then we also plot x against y in that case, and then we see the continuous deformation that causes a circle to be transformed into an ellipse, and that's exactly what we have here. When t is 0, the circle remains. When t is 0.33, the ellipse begins to form. I mean, this is no longer a circle. In fact, it's already an ellipse. By t is 0.67. Now, this is where all this 0, 1 over 3, 2 over 3, this is 0, 0.33, 0.67, and 1. So at 1, so in fact, from this next step, it's already an ellipse. It's from the first, once t is applied, it already gets reshaped into an ellipse in that sense. So we see that that's the continuous transformation, deformation that topology is about. Shape can change while topology remains unchanged. Then we talk about, so in this case now, the circle and ellipse they are homeomorphic, that is, they are topologically equivalent. So let's do the historical synthesis of everything we've been looking at now. You see here now that we see here that the history of topology illustrates a fundamental transformation in mathematical thinking. Euler showed that a problem that looks geometric may actually depend only on connectivity. Möbius showed that surfaces can possess surprising global properties such as one-sidedness. Poincaré showed that geometric spaces can be studied using algebraic structures. Hausdorff helped formulate topology axiomatically and abstractly. Brouwer demonstrated that continuous maps obey powerful global principles concerning fixed points, dimension, and domains. The resulting mathematical philosophy can be summarized as topology studies what survives continuous deformation. So the historical developments can therefore be represented as Euler to Möbius to Poincaré to Hausdorff and then Brouwer. But this was not a simple linear regression. Many other mathematicians contributed to the development of topology, including people like Bernhard Riemann, George Cantor, Camille Jordan, Walter von Dyck, and Oswald Veblen, James Waddell Alexander, Pavel Alexandrov, Heinz Hopf. Their work contributed to the modern theories of point set topology, algebraic topology, differential topology, geometric topology, manifold theory, homotopy theory, and homology theory. So, and why the history of topology matters. Studying the history of topology is not merely historical background. It explains why the subject has its characteristic concepts. So Euler talked about led us to connectivity. Euler's bridges problem motivates the study of connectivity and graphs. Möbius leading to global structure. The Möbius strip demonstrate that global properties may not be obvious from local appearance. Poincaré told us about invariants. Poincaré motivated the use of algebraic invariants to distinguish spaces. Then we have Hausdorff and his axioms. Hausdorff's work shows how topology can be defined without relying on pictures. Then we have Brouwer, who began with the idea of continuous maps. Brouwer demonstrated that continuous functions can force strong global conclusions. Therefore, many modern topological concepts can be understood historically, starting from connectedness to holes to invariants to topological spaces to continuous maps. So topology is consequently not simply a collection of definitions. It is a combination of a long mathematical search for the essential structure underlying geometric objects. So what are our key takeaways from all of these stories? Euler helped initiate topological thinking by replacing geometry geometric details with connectivity information. Then the Königsberg bridges problem demonstrated that some geometric problems can be solved using graph structure alone. Euler's polyhedra relation tells us that vertices minus edges plus faces is equal to 2. That became closely connected with the modern Euler characteristic. Then Möbius introduced the famous Möbius strip illustrating non-orientability. Poincaré established foundational ideas in algebraic topology and introduced powerful ways to associate algebraic structures with spaces. Hausdorff helped establish an axiomatic framework for topology and introduced the Hausdorff separation condition. Then Brouwer developed major results concerning fixed points, dimension, and invariance. The historical development moved from concrete geometric objects toward increasingly abstract spaces. So a central topological idea is that properties can remain unchanged under continuous deformation. So the modern subject of topology combines geometry, algebra, analysis, set theory, and combinatorics. The historical journey can be remembered as connectivity to surfaces, to invariants, to axioms, continuous maps. So this journey leads directly into the modern study of topological spaces. And then we come to our problems as usual. So here you can see up to problem 9 clearly. So in like I did with other videos, I'm just going to uh, verbally talk about the ones I will answer. So let me talk about, I'll be talking about 10. So question 10 says, consider a figure 8 space formed by joining two circles at exactly one point. Determine its first Betty number B1, beta 1, and explain what the result says about its independent one-dimensional cycles. So for a figure 8 space consists of two circles joined at a single common point. Then each circle contains one independent one-dimensional cycle. Then since the two loops cannot be continuously deformed into one another, they contribute independently to the first homology group. So a figure 8 space is simply a figure 8 space consists of two circles, right? Two circles joined in the center. Something like this. I hope I can do justice to that. So let's say this is the center of this circle. And then we have another circle like this, whose center is somewhere around here. So that's what a figure 8 space is. So a figure 8 space consists of two circles joined at a single common point. Oh, sorry. I think this is not the picture. So it should be, you have the circle and then you have, that's a challenge now. So I have this other one, something like this. So it's more like it forms a kind of figure 8 like this. So that's what a figure 8 space is. So a figure 8 space consists of two circles joined at a single common point. So they are joined at this single common point here. So each circle contains one independent, one-dimensional cycle. So uh so this is one independent one-dimensional cycle. This is another one independent one-dimensional cycle for each circle. So since the two loops cannot be continuously deformed into one another, so you cannot deform them into one another, they contribute independently to the first homology group. Therefore, the first Betty number beta 1 for this is 2. That's the one from each one. So more precisely, its first homology group is H1 of X, which is homeomorphic to Z plus Z like this. So integer, integer. You know, each circle is mapped to integer, if you remember. So it's homeomorphic. So H1 of X is homeomorphic to integer plus integer like this. So the two copies of Z correspond to the two independent loops. So this contrasts with a single circle for which, so if you have a single circle, beta 1 would have been 1 easily. Thus, the first Betty number provides a numerical way of detecting the number of independent one-dimensional cycles in this example. So the important topological idea is that a figure 8 has two independent ways of going around a hole. So these cycles are not eliminated merely by continuously deforming the shape. So no matter how well we deform this shape, as far as it is connected here, even if we deform them into separate ellipses, we have them doing their own thing, contributing to the overall thing, to the overall behavior as the deformation goes on. So in this case, now we see that beta 1 of figure 8 is simply 2 because it aggregates the behavior of each circle individually. So the other problem I would like to talk about is problem, I think that's problem 20 or so. So problem 19, so which we can all see here now. Problem 19 says, explain why Hausdorffness is useful when discussing limits. Construct an argument showing why a sequence cannot have two different limits in a Hausdorff space. So that's 19 now. So now we have learned something new, a figure 8 space. So this is a figure 8 space, figure 8 space. So it's a figure 8 space is formed when you join two cycles at a common point, basically. So never knew that until I came on this. So figure 19 says, problem 19 says, explain why Hausdorffness is useful when discussing limits. Construct an argument showing why a sequence cannot have two different limits in a Hausdorff space. So suppose X is a Hausdorff space and a sequence Xn. So let's say X is a Hausdorff space, Hausdorff space, and we have a sequence Xn converges, sequence Xn converges to two points, X and Y. So we want to show that, X is equal to Y. We need to show this. So if we assume for contradiction, we can prove by contradiction. Assume for contradiction, if we assume that X is not equal to Y. So because X is Hausdorff, there exist disjoint open neighborhoods U and V such that X belongs to U and Y belongs to V, and U intersection V is empty. Okay, that's what Hausdorff says. So that, and for this to have happened, we have to assume that X is not equal to Y. So what we want to prove that is that X is equal to Y. But if we go by contradiction, we say X is not equal to Y, then we can apply the Hausdorff law to it. So since X sub n converges to X, then it means that means that there exists an integer n1, that's an integer n1, such that for every n which is greater than or equal to that n1, we then have an xn belonging to U. So similarly, we also know that x converges to y, xn converges to y. So since xn converges to y, then there exists another n2, there exists n2, which is also an integer, such that for all n greater than or equal to n2, xn also belongs to V. So going afterwards, then if you now choose n to be greater than or equal to the bigger between n1 and n2. So if we make that choice like that, um so if we choose n to, which is the bigger of n1 and n2, then xn must belong to both U and V. So we can say that xn is an element of U. Xn is an element of U intersection n. U intersection n, which is supposed to be empty normally. So, but if that is the case, that contradicts Hausdorff, right? But this contradicts the fact that U intersection V should be empty. That's what the Hausdorff thing says. Therefore, our assumptions that X, so therefore, our assumption that x is not equal to y is actually false. Our assumption that x is equal to y is false. By contradiction, we've been able to prove that. Hence, we can say x is equal to y in that sense. So, thus, every convergence sequence in a Hausdorff space has a unique limit. Every convergence sequence in a Hausdorff space has a unique limit. So, this illustrates why Hausdorffness is an important separation property. It ensures that distinct points can be distinguished strongly enough that convergence cannot ambiguously approach two different limits. So, let me finish with this statement that every every convergent sequence, every convergent sequence, every convergent sequence Hausdorff, in a Hausdorff space has a unique limit, has a unique limit. And that's it. So with this, we come to the end of this interesting video about the history of topology. So again, look at the problems, try your hands on them, give mathematical justifications for all of this. So you have questions 1 to 10 showing straight up there. And then you also have questions 11 to 20. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you haven't subscribed, this is a good time to go ahead and subscribe. Um, and also hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join. That gives you some special privileges that you find out as you click on join. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.